أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. As we have already discussed that there are two types of wireless threading model. One is large scale threading model and another is a small scale threading model. And we have already discussed mostly are the large scale threading model. And two rays ground reflected is also a large scale threading model. And this model is a very simple propagation model used in wireless communication. And it considers both direct reflect line of sight and another is only single ground reflected path to describe the signal propagation. So today unit, firstly we introduce the model and then we discuss about the geometry of the model and we drive to the large difference approximation which we'll use for the further approximation to drive the received power equation. And finally, we try to determine the total power received at the receiver. And lastly, we conclude the two range ground reflected model. For the geometry of two range reflected model, assume a transmitter is height H above a flat smooth ground and a receiver is at height HR above the ground. And the distance between transmitter and receiver is R, which is shown in figure. Let the reflection coefficient of the ground G, and the reflection coefficient it can be defined as the ratio of the reflected electric field to the incident electric field. There are two paths of a ground wave to take from transmitter to receiver. One is the direct path, which can be represented by the R, and another is the length of the direct path towards ground R1, and that from reflected path R2. So the laws of reflection requires the angle of incident is equal to the angle of reflection. The result is that the reflected modified appears to come from a mirror image of the source as a distance at t below the ground. If you carefully observe the given diagram, you will realize that R1, R2, and R they are making some right angle triangle. And Pythagoras theorem can be applied, which is c square is equal to a square plus b square. So with the help of Pythagoras theorem, we calculate R1 is equal to R square plus HP minus HR bracket close square and all are under root. And similarly, R2 is equal to under root R square plus HP plus HR bracket close square. So here you will see that we can use the Taylor series approximation, which can say that under root 1 plus x can be approximately equal to the 1 plus x over 2. So by applying this approximation, R1 can be written as R is equal to HP minus HR squared divided by 2R. And similarly, R2 is equal to R plus HP plus HR squared divided by 2R. So the difference of R1 and R2 can be calculated and if you because R is cancelled. So difference of R is equal to 2 HTHR divided by R. So why we are calculating the path difference? So this path difference is used for the approximation derivation of electric field and then path power required for the receiver side. In fact, the receiver can see two transmitters at a time. The real transmitter above the ground and a virtual or the mirror image transmitting after reflected from the ground. The intensity of each these two uh, signals in the absence of the other would be given from the phase equation. So we you applying phase equation, we calculate the PR is equal to PT, GT, GR, lambda squared divided by 4 pi squared and 1 over R squared, where PT is the total power generated yeah, radiated by an isotropic source. BT is a transmitter antenna gain in decibels and GR is the received antenna gain in decibels. R is basically the distance between transmitting antenna and receiving antenna. And similarly, R2 is the distance between the ground and receiving antenna, and lambda is equal to wavelength of carrier in meters. Similarly, we can also calculate the power received after reflecting the ground, which is equal to the PR2 is equal to PT, GT, GR, lambda square divided by 4 pi square, multiplied by 1 over R square, where R2 square, where R2 is the distance between ground and received antenna. As you know that power cannot be added to each other. So we have to convert power into electric field by applying some factors, and then we can add these two electric field to calculate the final power received by the receiver. When both are present, we cannot simply add the power because it is electromagnetic field then can add and the field have both amplitude and phase. The amplitude is proportional to the square root of the intensity and the phase is a distance times. So the distance traveled in wavelengths. So the amplitude of the reflected field can also be calculated by multiplying by the reflection coefficient of the ground. So the total power proportional to the magnitude square of this total field. It can be written as PR is equal to PT GT GR lambda square divided by 4 pi square and modulus is that e power minus k 2 pi divided by lambda R1 divided by R1 plus the reflection coefficient e power minus j2 pi lambda R2 divided by R2 and modulus square. So here we can approximate this modulus and we can write as PR is equal to PT GT GR lambda square divided by 2 pi R square sine square 2 pi HTH half divided by lambda. Here it is important thing that sine is a trigonometric function and it oscillates between 0 and 1 while the envelope ETGTGR lambda uh, square divided by 2 pi R square it basically has the 1 over R square of behavior for free space propagation. So the approximation sine 1 over x square is equal to 1 over s square. Very good approximation, and we can simplify it as PR is equal to PTGTGR HT square HR square divided by R power 4. Here, two things are very important to observe. First thing is that the received power is falling off at 1 over R power 4, much faster than the free space or phase equation. And similarly, there is no wavelength dependency. The total power received at the receiver after two-way deflection is not a function of a wavelength. It is a direct function of the transmitted power, gain of the transmitter, receiver gain, height of the transmitter, and height of the receiver, and the distance between transmitter and receiver. So finally, we can say that this is analytical equation, not like all other wide scale, large scale trading models, which are mostly mathematically, for example, free space equation, whether Okumura or Hatha model and Professor model, they are some correlation equation. It is also analytical model. They drive the equation on the basis of only two signals, the wireless signal. One is a direct, another is a reflected. In actual practice, receiver received many signals due to the path reflections or path propagation. Many this receiver received signal. So actually, these two-way path reflect ground reflected model is very approximate model, but still it is a good contribution for approximation to calculate the power received from the receiver by either the transmitter or the ground reflected, either transmitter and the ground reflected. The two rays reflected model provides a simplified representation of radio wave propagation in outdoor environment by considering the direct and the reflected path as the primary component of the received signal. While the model offers basic understanding of signal propagation, it has certain limitations such as simplification, sometimes oversimplification. The two-rays model neglect the other propagation phenomena such as refraction, scattering, and multipath interference. In reality, these effects can significantly impact signal propagation, especially in complex urban environment with multiple obstruction. And similarly, the two-rays model assume ideal condition, including the perfect reflection and absence of other propagation effects. However, in ground reality, obstacle may have a varying degree of reflectivity, and our Earth is not very good at reflection. So absorption is also taking place by that. So leading to a more complex signal propagation environment. So all of these effects create some limited accuracy of this model due to the simplified nature. The two-range model may not provide accurate prediction of signal strength and coverage in all scenarios. Real-world propagation models that consider a broader range of factors are usually required for more precise analysis and design of wireless communication systems. Finally, we can say that two-way reflected model offer a straightforward approach to understand radio wave propagation. It should be used with caution and supplemented with many other sophisticated models when dealing with a complex environment or when higher accuracy is needed. Thank you.